It's my pleasure to introduce our next speaker, Divesh Aggarwal, who is not only a well-known researcher but also a good friend. Divesh is an associate professor at the Department of Computer Science and a principal investigator at the Center for Quantum Technologies at the National University of Singapore. He earned his PhD at ETH Zurich. His research spans lattice-based cryptography, pseudo-randomness, computational complexity, and coding theory. His key contributions include the fastest known algorithms for many different lattice problems and advancing the understanding of their computational hardness. His work also includes state of the art constructions in non malleable codes and extractors, which play a crucial role in many cryptographic protocols. In recognition of his research, he was awarded the NRF Investigatorship in 2024. So we're very happy to have him here. And also for those in Chennai, he's going to be around next week. So you can also, talk to him anytime next week. Over to you.
So thanks a lot, Shweta, for inviting me and for the great introduction. And this is an amazing initiative, and hopefully we'll see a lot of success over the next few years. Okay, so today I'll be talking about this work. It's kind of a survey talk, basically, where I'm talking about lattice problems and kind of looking at them from a slightly different perspective than what people usually think of computational problems. Like when we talk about computational problems, we typically think of polynomial, like basically we restrict ourselves to polynomial time. Either we talk about polynomial time reductions or polynomial time algorithms, or we'd say that, like when we say that a certain problem is hard, we typically mean that there's no polynomial time algorithm, right? For example, when we say that P is not equal to NP, implies that there's no polynomial time algorithm for certain problem. When we say that a problem is cryptographically hard, we assume that there's no polynomial time algorithm to solve this problem. But what people typically care about in practice when we are thinking of, let's say, crypto systems is we really want to understand how hard it is. Like just being not solvable by a polynomial time algorithm is not necessarily enough. Okay, so here's a brief overview of my talk. I'll begin by introducing lattice problems and kind of talking about what is known if we restrict ourselves to the standard setting, polynomial time. Like that's kind of what I'll begin with, and then I'll talk about kind of what we can say when we go beyond polynomial time, like talk about exponential time algorithms. I mean, here when I'm saying algorithms, I mean deterministic or randomized algorithms, but also non-deterministic algorithms, and then reductions. And then even if we take that viewpoint, I'll mention there's some concern with these reductions, and then I'll present an alternate viewpoint. So this is essentially, the whole talk is more or less about changing the viewpoint and just re-looking at the state of the art and kind of seeing what we can say. Most of the content is going to be quite simple. I mean, you can interrupt me and ask questions during the talk. Like, you don't have to wait till the end. Being interactive is generally more fun. Okay, so start with introducing lattice problems. So what is a lattice? A lattice, very simply put, is a discrete subgroup of n-dimensional real space, like R to the n. So for example, if you want to draw it in 2 dimensions, this is how it will look like. It's like a grid-like structure where I mean, for example, the simplest lattice is the lattice of integers in n-dimensional integer vectors, right? In general, more generally, the lattice is specified by a set of basis vectors b1 to bn. So for example, here is a picture of a 2-dimensional lattice with basis b1 and b2, right? And you can see that all integer combinations of these basis vectors are basically lattice vectors. So like 2b1 plus b2, 2b1 plus 3b2, I mean, like all integer combinations, right? More generally, the lattice is an integer times b1 plus an integer times b2 plus an integer times b3 and so on. So you look at all such vectors, infinitely many, but countably infinite. So these are what defines this lattice, right? Okay, so what is the lattice problems that we consider? The most important, the most fundamental lattice problem that we want to think about is what is called the shortest vector problem. So what is this problem? Here you are given a lattice, you'll be specifying the lattice via the basis. So you are given n basis vectors and you want to find a shortest non-zero vector in the lattice. For example, in this picture, this vector v is the shortest non-zero vector. So of course 0 is the shortest vector, right? But we are not interested in 0, we want to find the shortest non-zero vector. And I'll denote by lambda 1 the length of this vector. So this lambda 1 will show up many times, so just like remember that this is the shortest vector. This is the length of the shortest vector. And when I say gamma SVP, what I mean is the problem where we want to not necessarily find the shortest lattice vector, but find a vector which is a gamma approximation of the shortest lattice vector, which means it is fine to find a vector that is at most gamma times lambda 1 length. So we are okay to relax it by a factor gamma, right? So for example, if you think of this circle, or in general in n-dimensional, an n-dimensional ball of radius gamma times lambda 1, we are okay with finding any vector inside this ball, right? There are in n-dimensional space there can be exponentially many vectors. We are happy with finding any one of them, right? Okay, so SVP is a hard problem. It is NP hard. Let me just give you like as much intuition as I can possibly give on this two-dimensional planar surface. Like basically for a two-dimensional lattice, a basis basically can look like the nice basis that we had earlier, but it can also look like the basis like this, right? B1 and B2. And imagine that you are just given B1 and B2 and not really given the lattice vectors. When you look at that, it's much harder to spot where the short vectors are, like in this lattice, in particular finding the shortest vector. And this picture becomes way more complicated when you think of n dimensions. And I mean, actually for 2 dimensions there are smart algorithms that can find the shortest vector in polynomial time, but for n dimensions basically it's an NP hard problem. You cannot really find an efficient algorithm. Another very important problem for lattices is what is called the closest vector problem. Here you are again given a lattice specified by the basis, and you are given a target vector. This target vector can be anywhere in the n-dimensional space, not necessarily a lattice vector, and the goal is to find the closest lattice vector to this target. Yes? Yes. Factoring is large number is not NP hard. For it is not NP hard, it is believed to be computationally hard in the sense that people at least believe that there is no efficient classical factoring algorithm, but it's not NP hard. In particular, you can prove that it is in what is called NP intersection co-NP if you define it as an appropriate decision problem, and so we don't expect this to be NP hard, right? I mean, basically this from under standard complexity theoretic assumptions, actually factoring is not NP hard. But in what context do you want to ask? We don't believe we know it. There is a quantum algorithm. I mean, whether we will have large scale quantum computers that will actually implement it is like you can say that we believe that this will happen, but there is an algorithm.
Why do you consider the shortest vector problem as quantum safe?
Okay, one can give different answers to this question, but I think the right answer is we just don't know any quantum algorithm for this problem. And since it has such a geometric structure, and typically we have seen quantum advantage for problems which have a nice algebraic structure, which is not there in this problem, right? Basically, so typically for geometric problems we have not been able to exploit any get any quantum advantage. So that's why I mean there's no proof that you cannot have a quantum algorithm for SVP.
In fact, many people conjecture that such a quantum algorithm will exist.
Yeah, actually there have been many attempts in the recent times, like many failed attempts, but they have been people have been trying to kind of come up with a quantum algorithm. Yeah. So okay. So no. So not for the NP hard version, but as you see, like basically this SVP, we can define it with gamma approximation, and it's also interesting actually for the it's cryptographically relevant when gamma is a polynomial in n, and for that variant we can have like potentially quantum algorithms. I mean, this is not ruled out. For NP hard problems, sure, we don't expect quantum algorithms. Yeah. Especially if you want to talk about public key cryptography or even one-way functions, we don't know how to base. Yeah. Okay. So closest vector problem. So here the goal is you want to find the nearest vector to this target vector, right? I mean, so you're given a basis, given a target vector, and you want to find the nearest lattice vector. So and when I say distance L comma t, this denotes the distance of the target vector to the nearest lattice vector. Sorry? Yeah, I mean, okay, I should have specified the norm, but since I'll not bother too much about it, like think of Euclidean norm, right? I mean, I'll not be, I mean, but you can define it for any norm in general. For mostly when we talk about this in cryptography, we typically think of the Euclidean norm. So let's just restrict ourselves to that. Okay. And then there's a variant of this problem which is called the bounded distance decoding problem. This is just CVP but with an additional promise that the target vector is close to the lattice. So the distance of the target vector to the lattice is small. So so typically it's like distance is lambda 1 of L with shortest vector divided by a factor gamma, and gamma is, you think of it as bigger than 2. So why you want it to be bigger than 2? So that like there is unique decoding. So so when you look at the nearest lattice vector, you cannot have more than 1, right? So it's, I mean, and this name really comes from basically the error correction code literature. There's an analog of this in error correction codes, and that's where the name comes from basically. And I mean, for lattices it doesn't seem like bounded distance decoding seems like the natural name, but just because the similar variant was already existing in the codes literature, and that's why kind of it got this name. Yeah, so this is a problem that actually we will care a lot about. So okay, and then the problem that we care, like this is probably the most important problem in cryptography, at least in the last 20 years. I mean this is without like, I mean, if you look at any crypto Eurogroup proceedings, I think maybe half the papers, I'm not exaggerating, okay, 1/3 1/3 would have LWE somewhere. Okay, fine, I mean like, we can check, but good fraction. Yeah. Okay, so learning with errors, what is this problem? It's essentially the bounded distance. It's a randomized variant of the bounded distance decoding problem that I just mentioned. So what is the problem? You have a secret S. So secret S is the vector that you need to find out. So this is and what you are given is these noisy samples. So you're given a vector A and inner product of AS plus some error, right? And you're given a bunch of these samples. So think of these as like M samples. M is something like polynomial in N, multiple samples, and the goal is to find S, right? Notice that if you did not have error, then this is a trivial problem. You can just solve it using Gaussian elimination, right? Straightforward. But with these errors, it becomes much harder. This, like in particular, we don't know how to kind of recover S. This is a hard problem. So as I said, this is essentially the average case version of BDD. How to view this? Let's think of a lattice where you are lattice which is generated by these column vectors of A, right? So the column vectors of A are the basis vectors, but additionally you basically append these with this P000, 0P00, like P times basically the fundamental basis vectors, right? And when you do this, then essentially what you are asking is this target T, think of it as AS plus E modulo P, and this is close to the lattice generated by these vectors. The column vectors of A, and these in this B. Basically, so this target is close to this lattice, and the goal is really to find the nearest vector. Finding the nearest vector would immediately give you S, which is the secret that you are interested in. Make sense? So this is very closely related to the bounded distance decoding. It's essentially an average case variant where basically the vectors, the matrix A is chosen at random and errors are chosen at random, right? As opposed to BDD, which was the worst case problem. The basis is arbitrary and the shift is arbitrary also. What's the reason? So because we want to look at modulo P, right? So this automatically, when you look at the lattice generated, so essentially what is a lattice, right? We take all vectors here and all of these vectors and look at all integer combinations. And taking integer combinations with these is effectively doing the modulo P operation, right? Good. Okay, so why do we care about lattice problems? So why are they interesting? Why do we have 1/3 or 1/4 or whatever fraction of the crypto proceedings? Because this is probably the most popular answer, at least at the moment. I mean, this was not the reason that people started looking at lattice problems. People started looking at lattice problems primarily because of the worst case to average case reductions. But yes, but I think they got popularity after IIT's result, and then Regev's result basically made it really, really popular. But since this is the most popular answer, let's kind of go with that. And so this is people really care about post-quantum cryptography. In particular, NSA in 2015 made this statement where basically they said our ultimate goal is to provide cost-effective security against a potential quantum computer, and so they said let's get a new suite of algorithms up to basically protect us from this upcoming quantum-resistant algorithm transition. Essentially, people believe that large-scale quantum computers might come up sometime in the future, and basically you want to protect yourself sufficiently in advance. And so this NIST, the National Institute of Standards and Technology in the US, initiated a standardization process in 2019 for identifying a post-quantum crypto system for widespread use. Right? This was initiated, and a bunch of submissions were received. This was basically the initial list of submissions. As you can see, most of the submissions, a large fraction of the submissions are actually lattice based, and then there was some code based, multivariate, hash based. This was I think there were 20 signature schemes and 49 key encryption, or basically encryption schemes. But then what survived after a scrutiny over a few years basically was mostly lattice based schemes. There was one hash based. Then they continued around with future for digital signatures, but essentially what people are relying the most on are lattice based schemes. Right? This is generally the state of the art, and so that's one motivation to care about lattice based cryptography. The other one is that this lattice based cryptography allows us what is called the worst case to average case reductions. What it means that we can basically base our cryptography on worst. So when we want to use cryptography, obviously we want to generate our public key randomly, so randomness is inherent, right? When we use them, but we want to base our crypto systems. I mean, it would be great if we can base them on worst case problems, because when we say that a problem is hard, we are much more comfortable saying that a worst case problem is hard than we are that an average case problem is hard, right? I mean, so, and what was amazing about lattices, and which is not true for pretty much any other public key crypto scheme, is that there are actually reductions from. So this you can say that if you can break this particular public key crypto scheme, then that means that you can essentially solve this worst case lattice problem that people believe is hard, right? That's a well-studied worst case lattice problem. So in particular, what people got was a reduction. So this was actually from the work by Oded Regev from 2005 got a reduction from approximating the shortest vector approximating SVP to solving the learning with errors problem. And so LWE, which we kind of believe is hard for average instances, and this is hard in the worst case, right? I mean, so what this reduction achieves is there's a polytime reduction from this approximating SVP to LWE. So here's a picture of what is known about the shortest vector problem, kind of before our work. Essentially, this is what is known in the polytime world. So in particular, what is known is that for approximating this problem up to a factor constant factor, this is NP hard. So we don't know how to so basically unless P is equal to NP, there is no polytime algorithm for solving SVP up to a constant factor. And then there are clear barriers for approximating this or for showing NP hardness up to a factor bigger than square root n. In particular, square root n approximate SVP is in co-NP, and square root n over log n is in co-AM. So that means we don't really believe that it's NP hard for those factors. And if you make the factor slightly larger, then you can suddenly build very useful cryptography from this. In particular, if you believe that n approximate SVP is hard, then you can build basically then you can build one-way functions from this. And if you believe that n to the 3 over 2 factor LW n over 3 n to the 3 over 2 factor SVP is hard, then we can show that LW is hard, and we can build public key crypto from here. And for classically, basically, if you believe that n squared SVP is hard, then we can, if it's hard classically, then again we get sorry. If it's hard means there's no polytime algorithm for this, then there's no polytime algorithm for LWE. Basically, that's what we are saying, right? And I mean, yeah. So they got NP hardness of SVP for L2 norm, right? I mean, yes. So, but what they got is, I mean, this is NP hard under randomized reductions, right? But for P greater than 2, they got it under deterministic reductions. Karp reduction. Yes. 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 Yes, but you can look at the lattice generated by this. You can get basically we are in m dimensions, right? So you can get m linearly independent vectors that are generated by these n plus m vectors. So you can there are standard algorithms that you can run. Start with these n plus m vectors, and you will get m linearly independent vectors that generate this lattice. Yeah. Yeah, exactly. I mean, you can define a group, so you can define by a basis, but you can also define it by a generating set of vectors. But it will still be discrete. In particular, think of it this way: it's still a subset of the integer lattice. All vectors are integers, right? So it cannot be denser than the integer lattice, right? Make sense? Good. Yes. Yeah, everywhere here, it's still hard, right? I mean, we don't know how to solve this. I mean, when the factor becomes that large, then we know how to solve this problem in polytime. 2 to the power n by 2? 2 to the power n by, this is actually smaller than 2 to the n over 2. But something between that, yeah. So there is a trade-off. I mean, basically in particular, the larger the factor, the easier the problem becomes. You can get a faster algorithm. So it's really a like smooth trade-off in this entire range, right? And I mean, this is like so pretty with this problem. I mean, you can teach a whole course on just this problem. Actually, we do that basically because it's so rich. I don't know of any other computational problem that has this range of kind of what you can say about this problem, right? But this is not the topic of this talk. But so we want to really understand what do we actually mean when we say hard, right? When we are talking about this world, we are saying no polytime algorithm. But I want to really kind of understand this slightly better, right? When we say P not equal to NP, we mean SAT has no, P not equal to NP implies SAT has no polytime algorithm because SAT is NP complete, right? I mean, but then what is well studied now, it's been almost 20 plus years since this has been studied, like what is called the exponential time hypothesis, where we make the assumption that 3SAT has no sub-exponential time algorithm. So that's a much stronger assumption than this one, which says that it has no polynomial time algorithm. Now we are saying that the best algorithm has to be exponential. It's 2 to the Cn for some constant c, right? So this is a very widely believed assumption. I mean, in particular, for so many years of research, I mean, we've not been able to find a better algorithm. So we believe that this is hard, and kind of we base a lot of conclusions on this assumption. And then there is an even stronger assumption, which says that, which is called the strong exponential time hypothesis, which says that the constant in the exponent is essentially 1. Basically, it says that SAT has no 2 to the 0.99 n algorithm, n time algorithm, and I can replace SAT here by KSAT for a large enough k, and still the same assumption holds. So if you talk about what people believe, I think ETH is believed probably a little bit more than SETH. SETH, there are people who might contest it a little bit, like say that this might or might not be true. But I think no one really contests that ETH probably. Good. So let's look at this picture again. The worst case to average case reduction. Now the best algorithms for n to the k SVP, based on all our understanding of this problem, are still exponential in n. So the best algorithms run in time exponential in n, no matter what the constant k is. Like obviously, the larger the constant k, the smaller will be the constant c. So there is a trade-off there, but these are still exponential in n. So this is the best state-of-the-art algorithm for this problem. Runs in time something like 2 to the n over 2k. So as you can see, if k becomes larger, this constant becomes smaller, right? And there is also like SETH hardness of SVP known for this, but this is for near exact SVP, right? Now, if we ask about what we can say about these reductions, when instead of poly time, we allow, let's say, 2 to the epsilon n time. And here think of epsilon as a really tiny constant, let's say 0.01. So that means that when we start with the 2 to the Cn hardness assumption, let's say that we assume that whatever is the best algorithm that we have for SVP, that's kind of, we cannot really improve that, we've tried hard enough, and we believe that this is really correct. And then what can we conclude about LWE? So if we allow 2 to the epsilon n time for this reduction, then that would mean that LWE is hard up to a factor 2 to the c minus epsilon n. Just the same similar way as we conclude, like as we do for NP hardness reductions, we can do the same here, and we basically get that under this assumption that n to the k SVP cannot be solved in better than 2 to the c n time, we get that LWE cannot be solved in better than 2 to the c minus epsilon n time. So this brings us to the main statement that I want to make here, which is like talking about these problems where we allow ourselves more than polynomial time. So remember that this was our polytime world. And now when we allow 2 to the epsilon n time, the picture shifts. This is what we can show. So there is a co-AM protocol when the factor gamma is a constant. Instead of square root n over log n, we get a constant factor. But I am allowing this much time. So there is a co-AM protocol where the verifier runs in time 2 to the epsilon n, and we can get a co-AM protocol for SVP with approximation factor a constant, right? And similarly, we can what we can get in the 2 to the epsilon n world, which we are not able to get in this world, is also a co-MA protocol. If you don't care about the distinction between AM and MA, you can just forget about that. But like essentially, we can improve that to co-MA instead of co-AM. And then for co-NP, we can get we can basically solve SVP square root log n. Basically, I mean basically the complementary problem, the negation of SVP with factor square root log n in co-NP. I should not say co-NP here because we're not talking polynomial time. The verifier is really epsilon n, but just to be consistent, I'm kind of calling it to co-NP. So if strictly speaking, that's not really co-NP. And then what is very interesting is that if we allow this much time, we can actually start with a harder problem in some sense, right? We can start with SVP with square root n factor, and from that we can get the hardness of SIS, which means we can get one-way functions assuming square root n SVP is hard. And similarly, for LWE also we can get a square root n factor improvement. We can start with n approximate SVP, and we can get that LWE is hard if we allow ourselves 2 to the epsilon n time. So in particular, across all these reductions, we are improving by a factor which is something like square root n, roughly square root n, if we are allowing ourselves 2 to the epsilon n time. Yes, correct. Yes, I mean, I'm just thinking of the reduction in this much time, so that the conclusion that we get. So in particular, let's just take a look at the reduction for LWE. Earlier we had a polytype reduction from n to the 1.5 SVP to LWE. What it meant is, let's say that we believe that n to the 1.5 approximate SVP is 2 to the 0.067 n hard. This is just plugging in the best algorithm and assuming that that's really the best possible, and that would give that LWE is 2 to the 0.067 n hard, right? Because basically, but now since we have a harder problem here, we can make a stronger assumption for this harder problem, and we get, and our reduction is taking this much time, so we'll shave off that factor, but we still get a better conclusion basically. So just by changing the perspective slightly, we can essentially revisit the reductions and kind of get something better. Of course, I mean some of these reductions actually, when you allow that much time, it's not so straightforward. It doesn't carry through immediately. You have to kind of work a little bit. For this talk, I will focus on the reductions where the reductions or the results which are kind of the simplest, which are easy to understand. So I'll just show some of these results. So in particular, one result that I will show is this co-AM protocol. So let me just say what essentially we are interested in. What is for example co-NP. What we are interested in is that the prover Arthur sorry this is no picture, yeah. So this is a prover. This should be Merlin. yeah. So the witness Merlin sends the witness, and then Arthur wants to output I mean, I think everything is fine except I should have said here Merlin. But other than that, yeah. So what we want to show is that the completeness, which is that if the distance of the target is large, right? The distance of a target from the lattice is large, then we want to say that there exists a witness W such that the verifier on seeing W and the input would output far, right? I mean, that's the completeness property. And soundness is basically if the distance is small, then we want to say that no matter what witness what witness Merlin produces, the verifier will always output close, right? That's what we want to say in the NP setting. Oops. Oh, this is like converted to PDF, is it? Oops. Oh, why did that happen? It was showing fine on my screen.
Do you want to connect your computer? I might have the.
Okay. Yeah, I think so.
I mean, we can just because you may not be happy. But the rest of it is actually.
Oh, rest of it is fine, is it? Is it just that?
Seems like it's.
Okay, then I can live with that. I think it's fine. No, it's okay. This is okay. It's okay. I think we can skip that slide. It's fine. If it's just that, then it's okay. Okay. Oh no, this is again also coming like that. Sorry. Okay, okay those two. Okay, then let me skip to the next one.
I'm also wondering if this is just an image. If I just do this, it's better, right?
I think.
Yeah. Okay, now that's. So I think it's readable now at least.
Yeah.
And there were only two slides. Only two.
Okay. Okay, so in the co-AM setting, which is the setting that I'll be talking about, basically Arthur sends a random message in the first round, and then Merlin produces a witness, and then Arthur is supposed to basically run the verifier on the input and the witness. This is a standard setting, right? And then basically say whether it accepts or rejects, right? And for the completeness, what we want to say is that there exists a witness such that the verifier basically says that this target is far, or outputs basically far. And for soundness, what we want is that no matter what the witness is, the verifier will output close with high probability, right? And here it's not here since there is randomness in the first message, so you don't output far or close with probability 1. You basically have a certain error. So think of it as, when I say with high probability, you can think of it as 2/3 or 1/3, or you can think of a larger probability. Doesn't really matter. Okay, so I think I had. Okay, so I want to talk about a co-AM protocol actually for SVP instead of CVP. So I was just mentioning CVP, but I'll actually present for SVP because it's just simpler, right? So here you are given as input the lattice basis, and let's say T star I denote as the shortest vector in the lattice, and consider the ball that is centered at 0 of radius square root n, and the ball that is centered at the shortest vector but also with the same radius, right? And when this shortest vector is far from the origin, like basically all the lattice vectors are pairwise far from each other, essentially, which is the same as saying that the shortest non-zero vector is large, then you can see that these balls are very nicely disjoint, right? I mean, they're kind of far apart and disjoint. We're looking at balls of radius root n, and the target, sorry, not the target, this is the shortest vector is at a far away distance, 10 times square root n, right? Whereas when when the distance between the origin and the shortest non-zero vector is small, is much smaller than square root n, think of it as epsilon times square root n, then these balls have a good overlap, right? The balls overlap quite a bit. So in particular, the volume of the overlap over the volume of one of the balls is kind of significant. Actually, in n dimensions, it's not very high, but this ratio is still like 2 to the minus epsilon squared n, something like that. So it's visible, at least in the exponential world, the overlap. So what it means for the protocol, my prover is always Earth. Okay, so what we do is we sample S to be a random vector of length at most square root n, right? And also we sample V, which is a lattice vector, right? So I mean, think of any sampling algorithm that would sample the lattice vector. There are known sampling algorithms. And then what Arthur sends to Merlin is S plus V. Not so much, no. So think of this like basically GPV or any algorithm that would sample some vector, right? And then what Arthur sends is S plus V, right? Now, if you see, when the shortest vector is large, then what Merlin has to do is Merlin has to guess what S is and what V is, right? And notice that if the shortest vector is large, so 0 and the shortest vector is far away from each other. In particular, if you look at these balls around all lattice vectors, they will all be far away from each other. So then Merlin can easily figure out what V is and then figure out what S is also, right? Because Merlin sees S plus V and Merlin just finds the nearest vector, which Merlin can easily do because these balls are really far apart, right? I mean, these balls are square root n radius, so essentially bigger than like S lies within the vector S. So this V plus S is essentially lying in a ball around V, around the vector V. So Merlin can easily figure out what S and V are. So in particular, Merlin will always give the correct answer, right? This is easy, straightforward. But when they are close enough, no matter what Merlin tries, Merlin will always be confused between, let's say, the vector V and its shift by the closest vector, because this S, the length of S, is much larger than the distance of V from the nearest vector. So there is a huge overlap between the ball around V and the ball shifted by the closest vector, similar to like the overlap between 0 and T star, right? I mean, this is similar to this ball. So there is no way that Merlin will be able to figure out. In particular, the probability that Merlin will hit the correct S happens with like probability 2 to the minus epsilon squared n. So Merlin is wrong with probability at least this much. So which means that if we allow ourselves enough time, then we will figure out the difference between the yes case and the no case. So, and this same idea can be used to also see the reduction from 1 over epsilon SVP to bounded distance decoding, and hence to LWE, because there are standard reductions from bounded distance decoding to LWE. In particular, this was one of the main results shown by the paper that introduced LWE, the paper by Arvind Raghunathan. So I will not talk about the reduction from bounded distance decoding to LWE, but let me say how you can use the same idea to get from 1 over epsilon SVP to BDD. So what you have is again the input is the lattice vector L and T star is the shortest vector, and you are looking at these balls. Again, the same argument, right? If T star is far apart from 0, if the shortest vector is long, then these balls of radius square root n around 0 and T star are disjoint and in particular very far away from each other. But if T star is short, then these balls have a huge overlap. And so what we can do is we can replace Merlin by a BDD oracle, and we will still do exactly the same job. In particular, remember that what we needed to do was that in the far case, we wanted to figure out what V is, which was essentially solving the closest vector problem, and under the promise that the closest vector is quite close to the lattice vector, which is true here because the shortest vector is large. If the shortest vector is large, then clearly the length of S is much smaller than the length of the shortest vector. So the BDD oracle promise is fulfilled, hence it always gives the correct answer, right? And if the shortest vector has a small length, if it is at most square root epsilon times square root n, then this BDD oracle, the promise is not fulfilled. It might not behave correctly, but no matter how it behaves, we again have the same thing, right? BDD oracle will just not be able to figure out the correct answer, so it will be wrong with probability at least 2 to the minus epsilon squared, and exactly the same argument. I mean in the no case we are talking about something weaker than Merlin, so of course the same guarantee still holds. Good. So that essentially, I mean those were the two results that I wanted to show in the picture. These are kind of very simple ideas that I wanted to present. The other ideas are slightly more involved, so I didn't think that this was appropriate for this talk. But now I want to get to a third aspect of this talk, or the third part of my talk, which is essentially I want to point out a concern. Even when we talk about these reductions and we allow ourselves exponential time and whatever, there's still a concern with this reduction, and I want to talk about an alternate viewpoint that kind of partially at least alleviates this concern. So let me say what I mean. If you take a very close look at how these reductions look like, in these reductions from worst case lattice problems to the average case lattice problem LWE, so what happens is you start with a polynomial approximation of SVP, and you get to some kind of, so BDD again with the similar polynomial factor alpha, and then you reduce that to LWE. But if you look at the reduction, it reduces to LWE in the same number dimension n, but the modulus that you get when you look at this reduction, that is actually exponential in n. And then there are other results. In particular, there is this result by Brakarsky, Langlois, Pikert, Regev, and Stele from 2013 that basically shows that you can start with LWE with dimension n and modulus exponential in n to LWE with dimension n squared and modulus polynomial in n. If you compare this and this, you notice that the amount of information that is there, if you think of the entropy of the secret, that basically stays roughly the same. So, but we really care about kind of P being polynomial in n, because we eventually want to kind of use this in cryptography, and we want to kind of reduce this to the decision problem, for which we really need P to be polynomial in n. But that means that we start with dimension n, we end with dimension n squared. So even if we talk about kind of these reductions, I mean, and so on, we say that we have a worst case to average case reduction. What does it mean in a fine-grained sense? What does it mean? Okay, so notice that the best algorithm for LWE run in time something like 2 to the n. So you have a 2 to the n times log p divided by log n if you really care about the exact factor. So this is the result by Blum, Kalai, and Wasserman from 2000, and it's still the state of the art. This is the best algorithm for solving LWE, which is roughly exponential in n. But if we look at the best possible conjecture that we can make about these problems, we can say that these problems are exponentially hard. They run, the best possible algorithm runs in time like 2 to the constant times n. What does it mean about LWE? We would conclude that LWE in dimension n squared cannot be solved in better than time 2 to the n, which in particular means that if you just change n squared to n, you would essentially get LWE cannot be solved in less than 2 to the square root n time. So even if we make the strongest possible assumption here, what we get for LWE is not super strong. right? I mean, this is like 2 to the square root n. So which is the gap between what you are able to conclude from these worst case to average case reductions and what you want to conclude, which is that the algorithm that you have is really the best possible, is huge. This is not very, this does not seem very satisfactory, right? I mean, this gap in particular, and if you look at kind of, if we follow this thread that people discussed in this NIST, there is a mailing list around NIST. I mean, this is a complaint that like people who don't like lattices keep coming up with. This is a complaint that is very, very popular. I mean, not necessarily in these words, but something around these lines keeps coming up. Okay, so we would ideally want to close this gap. I mean, like this gap between what is the best algorithm and what is the best bound that we can prove. We want to close this gap. So for this, I want to kind of change the perspective a little bit. Okay, so what does this mean? So let's look at what do we mean when we say that a crypto system is, let's say, 256-bit secure. This is a standard notion that we kind of want to think about. We can think of it as like the fastest algorithm for whatever dimension n takes roughly, like, runs in time 2 to the 256. We can kind of think of it that way. But we can also think of it this way, that no reasonably efficient algorithm, let's say something that runs in 2 to the 50 time or something, can basically break the crypto system with probability greater than 2 to the minus 200. This is also a reasonable statement. I mean, if we assume that our adversary has only a limited amount of time, let's say, then probably we are happy with this kind of statement. And this is, I guess, what is more closer to what we usually want, right? I mean, it can be debated, but let's say we go with this B, right? I mean, which is no reasonably efficient algorithm can break the crypto system with probability greater than 2 to the minus 200. So we can, if we take that viewpoint, then we can introduce this alternative measure of computational hardness. This is actually a reasonably studied notion in computational complexity. I wouldn't say it's really popular, but at least there is some work around that. So which is looking at the maximum possible success probability for a probabilistic polynomial time algorithm that solves a problem. Instead of looking at the best running time, I am saying I will restrict myself to polynomial time and then ask what is the best success probability. For example, for SAT, this would be 1 over 2 to the n, right? You can just guess the solution. For Hamiltonian cycle, this would be 1 over n factorial. I don't know of anything better, for example, for Hamiltonian cycle. Even though you can solve it in 2 to the n time, if you kind of look at this, then the best success probability, then this changes the view of like the computational hardness of a problem to something that's different from what we were talking about earlier. Okay, so what does it mean for LWE? LWE, the success probability is basically you want to kind of you want to guess the secret or guess the error, like whatever the two, the success probability would be something like p to the minus o of n, right? And ideally we would want to get a lower bound that would look something similar in this setting, where I am now allowing myself polynomial time and I am asking what is the best success probability that I can get. So the question that we want to ask is, can we do much better? And I want to say that under a reasonable assumption about the worst case lattice problem, we cannot really do much better. So what is the best success probability that we can obtain for worst case lattice problems? For worst case lattice problems, based on my understanding of lattices from so many years, and this is something consistent with something I asked several people in the community. I mean, there's no proof for this, but the only algorithm that I can think of for solving SVP, if I'm given only polynomial time and I want to kind of maximize the success probability, is basically running this very famous Lenstra-Lowas algorithm and then guessing the coefficients. So what Lenstra-Lowas algorithm allows us is to essentially say that it changes the original basis into a nicer basis, where you can say that now the coefficient vector for the shortest vector is bounded. It's like all the coefficient vectors are bounded by something like 2 to the n, which essentially means that if you want to guess all of these coefficients, the success probability is going to be something like 2 to the minus n squared. You can do slightly better, so it's 2 to the minus n squared times log n divided by log n. So this is slightly smaller than 2 to the minus n squared. So I'm now saying that let's make this assumption that we cannot really solve SVP if I am only allowed polynomial time. I cannot solve it with success probability better than this. If you don't like this assumption, great, like basically break it. This is amazing. This would be amazing, right? I mean, so I mean, if you are like not happy with this assumption, that's actually a good news, right? I mean, then like let's try to find an algorithm that does better. That would teach us something about these lattice problems, which we don't know. So I'll call this a natural conjecture, and happy with the debate that like if we allow only polynomial time, then no algorithm can, let's say, solve BDD on an arbitrary n rank lattice where alpha is something like 1 over poly n. This is in time poly n with success probability better than 2 to the minus n squared log n divided by log n, right? So this is assumption that's coming straight away from the best algorithm that I can think of for this. And what we can show that if we make that assumption and we kind of revisit the reductions, the worst case to average case reductions, we look at it from this lens, like now we are allowing ourselves poly time, we are happy with losing like exponential factors in the success probability, suddenly like that's not a problem. We can actually get near tight reduction. So in particular, that conjecture would imply the maximum success probability for efficiently solving LWE looks something very close to what one would expect, which is p to the minus omega n over log squared n. Yeah, so there is so we can do a trade-off also. Like so you can get some nice conclusions still there. Probably weaker than whatever I have here, but yes, but you can get a trade-off. So I'm nearly also end of time. I mean, like so I'll end with a few open questions. I mean, I'll not really get into how to get that, but I'm really reusing ideas that are already there in the literature. So open questions: find new very interesting implications of these conjectures that one can say are very strong, but getting interesting conclusions from these would I think force us to basically understand these conjectures better, right? So in particular, the first conjecture I am stating is lattice problems even with poly n approximation factor are exponentially hard. I mean, this is just based on our understanding of these problems for so many years. Actually, this is a problem that people have tried really hard. I mean, this is a problem that would really affect cryptography, so people have really invested a lot of time on. So I think this is a more believable conjecture in some sense. I mean, because more time has been invested in trying to break it. So of course one should try to improve these algorithms, but also if we are not able to improve these, let's make this conjecture and let's kind of get interesting conclusions from this. Like, what can we conclude from there?
Yeah. What's the inclusion of, what's like a dream theme one could hope for?
So, I mean, people have built this whole theory of fine-grained complexity starting with the 3-SAT. And this here is a much more relaxed problem in the sense like you are allowing a large approximation factor. So you can maybe reduce.
Like in fine-grained cryptography points, the sort of thing you have is that you want a gap between the honest algorithm and the adversary. And typically there what we think of is that the adversary is also poly time, but like a larger poly. Now this kind of conjecture, which I completely believe, I'm not able to think, at least in these 3 seconds, that what might one hope for? Like, what would be the dream thing? Because
Okay, so when I'm talking about implications, I'm not really necessarily talking about cryptography implications. I'm talking about computational complexity implications also.
then I think there may be more.
I mean,
Anyway, it's more an open-ended thing. I was just thinking, like, from all the cryptography that I can think of, we pretty much
I was not necessarily suggesting cryptography. And then the other conjecture is like if I allow myself only poly time, then SVP cannot be solved with success probability better than 2 to the minus n squared, like ignoring those small factors. Can we get interesting conclusions from this? Can we understand this better? So I mean, for example, a related question that I was kind of saying, I did not have it on the slides, is for example Hamiltonian cycle. This is one example. The best polytime algorithm, if I want to talk about polytime algorithm and the best success probability, the only thing I can think of is like guess the cycle, which is like 1 over n factorial probability, right? Guess the sequence. But if you talk about the computational complexity of Hamiltonian cycle, you have a 2 to the n time algorithm. This is simple 2 to the n time algorithm. So in some sense, it feels like Hamiltonian cycle is in some sense maybe harder than SAT, like, or Hamiltonian cycle with the n being with the parameter n being the number of vertices seems harder than SAT where we replace the parameter by the number of variables, right? Because there both are like the running time, the best running time is 2 to the n, the best success probability is 1 over 2 to the n. So can we kind of understand this difference a little better and kind of say what we can conclude? For example, can we get nice conclusions from the statement that Hamiltonian cycle we cannot really get a success probability better than 1 over n factorial if we allow ourselves polytime? So I mean, yeah, so I wanted to kind of put these questions out in the open and see if anyone has.
So in the first one, I mean, you could take a lattice dimension which is smaller than security parameter, and then you can make this conjecture and try to get some fine rate.
Lattice dimension smaller than the security parameter, and then
Like when I earlier said that I can't think of what you can possibly do, I was thinking of a usual situation where the lattice dimension is the security parameter.
correct.
But if you want to think of fine grained cryptography, you could consider an adversary that runs in 2 to the n time, where n is the lattice dimension, but n could be, let's say, log squared n, log squared lambda or something like that. Like
I see.
if we work with a smaller lattice and make this conjecture, we might actually be able to get interesting cryptography.
Okay. Yeah. I mean, I have to think about because
No, so do I have to think. I'm
yeah.
just saying that there's a regime where something
I see.
could possibly be said.
Okay.
Because in the standard setting, this will not help.
I see. Yeah, sure. I mean, really open-ended, like basically what I want. Yes.
Basically, does this mean the second part, the discussion we had about this frequent SAT, does this mean that even polytime reductions don't guarantee that the success probability may have an exponential factor, exponential difference, for example, as frequent SAT, right?
So, sorry, I don't understand the question.
As in SVP and SAT are both NP hard.
Yes.
So they would have a polytime reduction with each other.
Correct.
But even then, okay, maybe not SVP, maybe it's Hamiltonian cycle.
Yes.
But you mentioned that Hamiltonian cycle probability, the success probability that we are able to think of is like 1 over n factorial.
Right.
Whereas for SAT, it's just 1 over 2.
So the problem there is that when you do these reductions, right, the reductions in the NP world, the reductions can have a blow up in the parameters. So in particular, when you reduce from Hamiltonian cycle to SAT, Hamiltonian cycle on n vertex graph would reduce to maybe n squared variable S SAT instance. And then the conclusion anyway changes, right? N factorial, like n becomes n squared. So
So does this mean we can have a, let's say, class of problems which can have similar success probabilities?
that's kind of what I'm trying to suggest. Yeah, I would like to say more than that. I mean, basically. So if there is something interesting that can be said, I will be happy to hear. Yes.
So one context where I've seen people is when you were studying in early days of doing geometry from standard alone, like getting this code like in sector and so on. I remember an assumption where they assumed that for specifically the Aggarwal encryption, secure against all polytime adversaries, such that the advantage is upper bounded by any support polynomial.
Okay. Okay.
So the flavor seems
I see. Yeah, this seems very similar.
Yeah,
I would say.
that sounds
favored by rank canopy glitch and
Yes, I see. I'm definitely not claiming that this is the only time that this kind of statement has been made.
No, no, he's just pointing
Sure.
another direction.
Yes.
But also like they do something like Shweta was saying, like they had to do some kind of complexity leverage. I don't remember whether it was exactly the log square lambda, but they had to do some kind of two security parameters,
Right.
and some kind of leverage.
So for example, this result that I was talking about, the reduction, right? One thing that we had to care about when we did this reduction is that I did not want to get into the details, but really, when you do the standard reduction for worst case lattice problem to LWE, you make polynomially many calls to the oracle. But polynomially many calls is very costly here. So what we did was basically did this whole thing with a single call to the, and we are okay with losing like exponential factor in the success probability. That's totally fine. But like making more calls is not. So in that sense we had to change the reductions. Yeah.
So in the interest of time, let's take further questions to the coffee break. Let's thank the speaker. As a small